while cleaning is no longer the core problem. With a wind tunnel-based smoke control system, improving smoke capture efficiency is only part of the story. It also opens a completely different approach to cleanliness. Instead of frequent cleaning, weekly or monthly disposable airflow paths become possible. Why? Because in this system, the smoke inlet itself is no longer a power source. It is simply a passive duct. All active airflow is generated by the airflow guide below. That means the highlighted duct section you see in this video can be made from low-cost, replaceable materials, as long as airflow is unobstructed. Once it gets dirty, you'll replace it, not clean it. This is not maintenance-free. It is maintenance-optional by design. The core of the system, the smoke locking airflow guide. At the heart of this wind tunnel smoke system is a compact but powerful device, the smoke locking airflow guide. Its motor is smaller than a coin. Its fan diameter is smaller than 3 fingers together. Yet it can capture cooking smoke quickly, precisely, and across a surprisingly large area. At first glance, this feels counterintuitive. But this is exactly where fluid dynamics becomes powerful. Small structures can activate very strong flow field effects. This device does not rely on suction. It relies on blowing fast, controlled blowing. Instead of moving large volumes of air, it creates a high-speed jet that builds airflow structure. The key is timing. Before smoke has its 0.2 seconds to disperse, it is guided into a predefined path. Now let's break down how this works, step by step, simply and scientifically. 1. Accelerating the airflow. A Venturi-like contraction, the airflow guide is powered by a small high-speed motor at the base. Air is blown upward. But to further increase jet velocity, we designed a converging section around the motor. While this is not a textbook Venturi tube, it follows the same physical principle. When cross-sectional area decreases, air velocity increases and static pressure drops. As a result, air exits the guide as a fast, focused, annular microjet with very clear directionality. At the center of this jet, we place a smooth, vertical stainless steel cylinder, called the guiding column. As the jet flows upward along this column, a chain of classic aerodynamic effects is triggered. 2. The Coandă effect. Why the jet climbs the column? One of the key phenomena here is the Coandă effect. High-speed airflow naturally tends to attach to nearby curved surfaces, rather than travel straight and disperse. Because the jet is both fast and annular, it automatically attaches to the surface of the guiding column and climbs upward along it. This creates 3 critical outcomes. 1. An invisible vertical airflow corridor forms around the column. 2. Flow direction becomes stable and well confined. Surrounding air is pulled in. To upward motion, this attached jet becomes the main highway that smoke will follow. 3. Multiple aerodynamic effects working together. The power of the airflow guide does not come from a single effect. It comes from multiple aerodynamic mechanisms occurring simultaneously, reinforcing each other and forming a stable boundary layer. Together, they lock smoke direction and suppress lateral dispersion. Let's break them down. 3.1 Entrainment effect. Low pressure pulls smoke in. According to Bernoulli's principle, higher air velocity means lower static pressure because the jet is extremely fast. A localized low pressure region forms around the guiding column. Surrounding air and smoke naturally move toward this low-pressure zone. This is why smoke appears to move toward the airflow guide, not because it is sucked, but because pressure gradients do the work. 3. To shear, entrainment, velocity differences create capture. Next to the fast jet is much slower moving smoke. Large velocity differences create shear layers, which generate small vortices. At the boundary, these vortices continuously pull smoke into the main jet, mix it into the high-speed flow, expand the effective capture region. A simple analogy: when a high-speed train passes, loose objects nearby are pulled into motion. 3. Sun induction effect, guiding the larger flow field. The jet doesn't affect just a few centimeters of air. It reshapes airflow patterns across a much larger region. Two dominant induced flows appear. Horizontally, surrounding air moves inward toward the column. Vertically, air near the column is guided upward. As a result, smoke is not chased. It is led into the path. This induced convergence is key to large area control. 3.4. Local rotational structure, stabilizing the upward path. As the jet climbs the column, geometry and velocity gradients introduce mild rotational components, not large vortices, but a subtle spiral-like airflow structure. This rotation stabilizes the upward motion, wraps smoke more tightly into the flow, reduces side leakage. Think of smoke being twisted into a rope and guided upward. 4. When everything combines, a smoke highway, high-speed jet Coandă, attachment entrainment, shear mixing, induction, local rotation. Together, these effects form a stable, high-speed airflow corridor. Smoke is automatically drawn in. Direction is fixed early. Flow is fast and stable. Dispersion is cut off at the source. Smoke enters this corridor before it has time to spread. This is the fundamental difference between the wind tunnel approach and traditional range hoods. 5. Core summary: from suction to path control. The airflow guide does not pull smoke toward itself. Instead, it builds an airflow path in advance, and smoke naturally enters it. Through structured jets, surface attachment, pressure gradients, induction, and shear entrainment, smoke dispersion is transformed into guided flow. This is a shift from passive suction to active trajectory control.